Band theory, p-n junctions, and the Fermi level. By the end of this lesson, you should understand what happens in terms of band theory when a p-n junction is formed and how it's affected in what's known as forward and reverse bias. In our previous lesson, we learned about the Fermi level. The Fermi level is the maximum permissible energy an electron can have at a temperature of absolute zero or minus 273 degrees Celsius. This means this is the maximum energy an electron can have if all heat energy is removed from the object. We also learned in our last lesson that when a semiconductor is doped, it affects the position of the Fermi level. For a p-type, the Fermi level is lower, and it's much closer to the valence band. For an n-type, the Fermi level is much higher, and it's closer towards the conduction band. In today's lesson, we're going to take a look at p-n junctions and how these two phenomena can be combined to create a better conductor. Let's take a look at the p-n junction. Looking at the diagram, we have the p-type semiconductor on the left-hand side and the n-type semiconductor on the right-hand side. These two types of semiconductor have been wafered together in the form of the p-n junction. Now, remembering back to that previous slide and remembering back to where the Fermi levels lay, now the Fermi levels have actually joined together. You can see that the Fermi level runs through the p-type, through this zone known as a depletion layer, and then through to the n-type. Now this zone is known as the depletion layer. We'll talk about in a wee minute. Now remember that the Fermi level is the maximum permissible energy an electron can have. With our n-type semiconductor doped the way it is, our Fermi level is quite high on this side, but also quite low on the p-type side. So whenever the electron gains that little bit of energy, it actually can cross very, very easily and pair up with a hole. So it allows conduction to take place. But for it to happen, the electron has to cross this zone known as the depletion layer. Now the depletion layer, this is a zone which forms as electrons migrate across from the n-type towards the p-type. Now we'll go into a little bit more detail in a second, but essentially as a depletion layer forms, it starts to prevent conduction taking place more and more gradually. The more electrons migrate across from the n-type to the p-type, the greater the depletion layer can become, unless we do something about it. But essentially, if the Fermi level still runs through the depletion layer, conduction can occur. This diagram is a representation of a p-n junction wafer. On the left we have the p-type semiconductor, and on the right we have the n-type semiconductor. Remember that the p-type is formed by introducing atoms which have 3 valence electrons in their outer shell. The n-type is made by introducing atoms with 5 electrons in their valence shell. Now bear in mind I keep on using the term atom, and I'm actually pronouncing it very, very carefully here. The atom essentially has equal numbers of protons and electrons. Now if you take a silicon lattice and then you dope it with, say, a p-type or an n-type semiconductor, you're still doping it with essentially an atom. So you can have a lattice of silicon atoms and then introduce an impurity atom. But when you do that, all these atoms, they all still have equal numbers of protons and electrons. So to begin with, the p-type semiconductor will be electrically neutral, and the n-type semiconductor will also be electrically neutral because these protons and electrons are balanced out. Now let's think back to how the p-type and n-type semiconductors are formed. A p-type semiconductor is formed when impurity atoms with 3 valence electrons are introduced into a lattice structure, say silicon. Silicon has 4 valence electrons and the impurity would have 3 valence electrons. In grand total, that gives you 7 electrons in its outer shell, which leaves this hole in its outer shell that other electrons want to fall into. The formation of the n-type semiconductor, that's when you introduce an impurity with 5 valence electrons into a silicon lattice, and the silicon atoms could all have 4 valence electrons there. 4 plus 5 gives you 9. Now remember, a full outer orbital can only have 8 electrons, so that gives you that free moving electron, and it wants to be bound to another outer shell. So even though both the n-type and the p-type semiconductor start off as electrically neutral, the electron in the n-type wants to migrate over and fill in that gap in the outer shell of the p-type semiconductors. So essentially the electrons want to bind with these holes, they fall into these holes. And then this happens. Whenever the electrons migrate over into the p-type semiconductor, essentially the p-type has now gained 3 extra electrons. There's an imbalance in the number of protons and electrons in total. With those 3 extra electrons, the p-type now becomes negatively charged. Because the n-type has lost those 3 electrons, it creates gaps or holes in themselves. And unless electrons can be brought into the n-type, then as a result, 3 new positive charges have now been created in the n-type. Over time, this can become a problem. As more and more electrons migrate from the n-type to the p-type, the negative charge on the p-type builds up more and more and more. And the same with the positive charge in the n-type. Now, the electrons are the free moving particles here. And if they are trying to migrate from the n-type to the p-type, and the p-type has too great a negative charge, well, you know that an electron has a negative charge. And if the p-type is also negatively charged, 2 negative charges will want to repel. So essentially what happens over time is a depletion layer forms. This creates a small potential difference. It sort of acts against the flow of the current. And if electrons can't pass this depletion layer, if the p-type is too negatively charged, then no conduction can take place. Depending on how the p-n junction is connected within a circuit, the depletion layer can either increase in size or it can decrease in size and break down. And we're going to take a look at 2 scenarios of this. In this scenario, we have a diode made up of a p-n junction, and it's connected in such a way that the n-type side of the semiconductor is connected to the negative terminal of the battery. Now, this helps a lot. You know the electrons from the n-type semiconductor will migrate over to the p-type, and as a result, holes are then left behind in the n-type. It starts creating a positive charge. But because it's connected to the negative terminal of the battery, electrons can then flow in and then replenish themselves in the n-type semiconductor. And this allows the depletion layer to collapse. Essentially what happens in the end as well is the electrons will continue to move. So imagine a constant flow going towards the left-hand side. And as a result, as the electron moves, any holes that are created move towards the right-hand side. So essentially you can think of it this way. The electrons are moving towards the positive terminal of the battery. And if you think about that gap, that positive charge of the hole moving towards the right-hand side, towards the negative terminal of the battery, you can therefore say that there is a flow of positive charge going towards the negative terminal of the battery if you're dealing in terms of holes. This is known as forward bias. So this allows the depletion layer to collapse. Looking at this in terms of band theory with the p-n junction connected to the battery correctly, you can see that there's actually a breakdown of the depletion layer here. The depletion layer is actually less steep. You can also see that the Fermi level of the n-type is much higher than the p-type. So essentially the electrons have enough energy to easily migrate across the depletion layer and pair with holes on the other side. In this scenario, the battery terminal has been reversed on the diode. The negative end has been connected to the p-type side of the semiconductor, and the positive end of the battery is connected to the n-type end of the semiconductor. Now, within the p-n junction itself, you still get electron hole migration naturally, and a depletion layer starts to build up. This is because the electrons pairing up with the holes in the p-type will start building up a negative charge within the p-type, leaving a positive charge within the n-type. And if electrons are trying to flow from the negative terminal of the battery towards the p-type, you're going to get electrostatic repulsion because of the 2 negative charges. In this instance, current cannot flow, and in this scenario, the diode has been connected in what's known as reverse bias. Looking at a p-n junction in reverse bias in terms of band theory now, you can see very, very clearly that the depletion layer has actually become very, very steep. You can also see that the Fermi levels themselves, they don't interconnect. They can't actually cross the depletion layer. And as a result, if the Fermi level cannot cross the depletion layer, the electrons will never have enough energy to cross from the n-type side of the semiconductor into the p-type side of the semiconductor. So the depletion layers become so great that no conduction can take place. To summarize some key points from our learning intention from the start of the lesson, whenever we combine a p-type semiconductor as a wafer with an n-type semiconductor, we form what is known as a p-n junction. Whenever the electrons migrate from the n-type side to the p-type side, a depletion layer can form. Both the n-type and p-type are essentially electrically neutral to begin with. Whenever the n-type loses electrons, it becomes positively charged. Whenever the p-type gains those electrons, it becomes negatively charged. In terms of band theory, so long as the Fermi level can cross the depletion layer, conduction can take place. Whenever a p-n junction is connected in forward bias, the depletion layer breaks down and conduction can take place. The Fermi levels of both p and n-type can cross the depletion layer very easily in terms of band theory. Whenever a p-n junction is connected in reverse bias, the depletion layer widens, which prevents conduction, and both Fermi levels of p-type and n-type cannot cross the depletion layer whenever we're looking at it in terms of band theory.